Okay, so there's no easy way of presenting this information. I'm going to be doing some cryptography in Prolog. A lot of people would say that you shouldn't do this, and they're mostly right. It's not a good idea. I've already done the coding for this project, so I'm going to be going a little bit faster than it would ordinarily be possible for somebody to go on a project like this, which is to say I'm not going to be doing that much testing because I've already done the testing. This is the command to invoke SWI-Prolog, which is the dialect of Prolog that I happen to like. It's a pretty popular one. It's probably the most fully featured one. Prolog itself, of course, is a language from the 1970s that probably shouldn't be seriously used, but for whatever reason you can still use it for things, and I occasionally do so. So every program starts with an entry point, and ours is going to start out pretty skeletal. We're just going to take a command, and in this case the command is actually empty, and we're going to make sure that we can see what the output of that command is. And that, of course, looks like this. As a side note, my cursor jumps around a lot on the screen because I'm using V keys. Also, if you don't tell Prolog to write the new line, it won't do the new line. So that's useful to know. Oh, hold up. That's not how you exit Prolog. That's how you exit Python. So Python is not a language from the 1970s, and that's a nice nicety of Windows. Apparently, the way that it starts on Windows involves a batch file that isn't well behaved. You'll also notice that Visual Studio Code thinks this is Perl. That's because both use the .pl extension. I'm actually using the Prolog editor extension, which ostensibly should change that behavior, but it doesn't. And you'll also notice that it struggles with double-quoted strings. This is how you would write a string in SWI-Prolog. The quote type actually does matter, but we're not going to get any help with that. So now that we've written this, we should be able to see, yes, that's how you get a program to output hello world in Prolog. And this took me a little bit more trial and error than you'd think because the initialization directive actually has several different syntaxes that you can use with it, and they have different behavior. So we're going to start with that, and we're also going to pull in from my sample project a couple files that are going to be used later. So the exact crypto system we're going to be implementing is called, it's a goddamn mouthful, XChaCha20 dash poly 1305, which is a series of words that have meaning, but not when you put them together in that order and arguably not separately, so I'm going to have to muddle through. The distinctive feature of this crypto system compared to some other crypto systems is that it allows for associated data, which is to say that I can encrypt my message and I can include context information about the message such that the message will be encrypted such that, well, I'll explain. There's a signing process. Signing is probably not exactly the right word. There's an authentication process would be the ordinary word for it, and it depends on this extra information. But right now, I just want to get all my folders into the directory, and apparently that was one of them. I've got another one here. Right. So we're going to be working with this key. Later, we'll get to the fact that this is a really bad way to initialize a key, the reason being that if I constrain my keys to only the keys that are 32 bytes of English text that that is the creator of this video, am likely to enter, then it's not going to be possible for most of the good keys to be used, and I'm vulnerable to all the attacks that assume that I used a bad key. 32 bytes is plenty for a key if your algorithm is really good, but if your way that you select keys is that you ask a person to type whatever words are on their mind currently, you're going to get really bad keys. So the center point of ChaCha20, because we'll just start coding and I'll explain it as I code, is what's called the ChaCha20 block function, which is to say that it's a function from about 512 bits, which is 64 bytes of text, to 64 more bytes of text that's going to be used in various ways. There are a few operations that are the core of the function. They are addition, which works the way that you would hopefully expect it to work. It looks like that. There's XOR, which you may have seen in other cryptographic algorithms. It's often beginners will use XOR by itself as a cryptographic algorithm because it's reversible. And we've also got this terrifyingly named function. I guess I'll give it a less scary name, but it has a very scary definition. So what this says is that when we rotate by amount, we take A0 and shift all the bits in it left by a certain amount, and we shift all the bits in it right by that amount rotated by 30. This is easier to see if you actually visualize it. So you might have a constant like this in hexadecimal, or we'll add there. Now it's 32 bits, which is the normal number of bits that a constant is. We would turn it into a constant that looks like, if we were to rotate it 4 bits, for instance, we could turn it into a constant that looks like this. And as you can see, the little f just moved over by 4 bits, which is how many bits one of these digits is. So yeah, these are the operations that Cha-Cha is based on, and they're a lot terser in C, which is hardly a surprise. C is designed for implementing algorithms like this. So the next thing that I want to focus on is the fact that Cha-Cha, because it is a function that maps 512 bits to 512 bits, which is to say it maps a string to a string, we're going to be using DCGs as our tool to implement it. We'll start with a base case for our algorithm. What this is, it's a function that takes a numerical value, a predicate, I should say. It takes a numerical value and it takes, thank you, VS Code, something which can have any type. It's just a variable named D, and it produces a variable named D. We're going to run into cases where that framing isn't helpful in understanding, but if we think of this as a function, we're doing okay. So I'm then going to write this definition, and I'll use a better name for this actually. We'll say block state. That's pretty good. So we'll say that this function maps block state 0 to block state of n. We'll also name this more helpfully round. So we want to do some specific work here. One, we already covered the case where there are no rounds left because this is a recursive function and we're going to be using it to implement the behavior of doing things a certain number of times. We've already handled the case where we're going to do it 0 more times. We're now handling the case where we're going to do it more than 0 more times. The reason that I check for this separately is that Prolog functions can return more than once, and if the first return completes, then if Prolog wants to see this function run a little bit more, it'll just jump to this second clause, which will make a little bit more sense later, or possibly it won't. Prolog's kind of like that. What I've just described is kind of the central feature of Prolog, which is that functions can return more than once. You'll also hear people insistently call them predicates. I'm using the word function because that's probably the word that anybody else would be familiar with, and it's a word that I use internally. But yes, so we're handling this other case, and because these cases have exclusive conditions, the first case, if it runs, the second case definitely will have the effect of doing nothing if Prolog resumes it. And if the second case runs, that means the first case already did not run. So we'll handle that case, and we'll do it like this. And we'll call the round function. Right. So what this does, just to summarize really quickly, and I apologize, this is difficult to explain and I'm not much of a teacher. We start with a round index that is passed to the Cha-Cha function. We also start with a block state that is passed in. We get an empty variable to put the final block state in. You'll notice that these are not marked in any way, but that's how it's going to happen to work. We take the round number, we subtract 1 from it, which is to say we use the add1 function, but instead of passing the first argument as a populated value, we pass the second argument as a populated value. Its definition, therefore, takes the first argument and puts the value of round 1 minus 1 into it. So this might equal 9 if round 1 was equal to 10. We then call the round predicate, which will take this empty variable and this full variable. It will use the contents of this full variable to populate this empty variable. Then it will recall the Cha-Cha predicate, starting from the new exciting full variable. And maybe that's what we want. So we then recall it, we get its final result, we put it into this block state n variable. So I'm going to do the first thing, sorry, the second thing that makes this really complicated. Prolog already makes this complicated. I'm going to rewrite the function definition to look like this. So this is a Prolog feature that is best explained by example, so follow my example here. These functions all took an extra argument, and this function takes 2 extra arguments right here, this predicate, excuse me. This has the effect of taking every case where we carry over these 2 arguments, basically every case where we go from an initial to final state using these last 2 arguments, and it just daisy chains them all together. It does exactly the rewrite that would get us back to the original version. To do that again in front of you so you can see it, originally this maps block state 0 to block state 1. It maps block state 1 to block state n. When we convert this to a DCG style function, it does the exact same thing, but with a lot less code. This is going to be important because I'm going to give you a real workout on this in a moment because we have the round function here. So the round predicate, again, it can be written like this. It maps some A to some B. And it does this by way of a quarter round function which takes some arguments, maps A to Z, and then you could say that another one maps Z to W, and so on until ultimately one maps W to B. That's the structure of the round function. We're going to write this as a DCG style function too. Effectively, we're going to give it a laundry list of 8 things to do. I already have the 8 things written down. There they are. Unfortunately, we don't have this qround function. What is qround? It's a quarter round. You'll notice that we actually do 8 quarter rounds, so I'm going to rename this to dround. The basic operation is to do a round, and there are 2 ways to do a round, meaning that this does a total of 2 rounds. Very exciting. Well, maybe. So we have this quarter round function which does a whole lot of math, and fortunately I have the math right beside me, so I'll show you the math. What it does is it takes the 2 values inside of our block, which consists of 64 bytes. It interprets the block as being 16 integer values, and then it does the math from these expressions to them. The best way to understand this is actually to look at the Cha-Cha spec, because then you'll see a copy of the code in C, which is a much better way to understand this than Prolog. You'll also be confused because there's no at function in this program. I'll show you what it does in a moment once I write it, but yes, the gist of it is that we have values A, B, C, and D, which are in variables. We populate A to equal A plus B, which is what we've written here. We populate D to equal D XOR A, and then we populate D to be D rotated. Oh, I renamed this function from my original version like this. Yes. So of course we've also got this at function, which I think I actually have to write for you. I think it would be cheating to just copy paste it, as much as, of course, there's a lot to explain here. So at is another function that maps the initial state of a thing to the final state of a thing. That is L0 to Ln. The specific way it does this is it consumes, in this case, a list that contains, as you'll remember, 16 elements. Might be good to have an example of that. We could say that state of Cha-Cha could look something like this. That this would be a reasonable way to represent it. There's 16 of them. Yes. And we're taking a state that looks something like this. I'll get rid of that in a moment, but right now it's here. We're pulling out whatever is at index A, which might be 0, then 1, 2, then 3 in the first sequence of quarter rounds. But we're taking whatever is in that particular spot, and we are actually getting its value. This is how you index an array or a list in Prolog. We're taking its value and we are mapping the list from its original state to a new list. So imagine if instead this list went 1, 2, 3. If we were to take nth0 of 1, 2, 3, and we use index 0, we would get the value 1 here, and we would get the value 2, 3 here. Very cool. Likewise, if we were to do it with the value 1, we'd get out the 2, and we'd get 1, 3, because this 2 goes away. That's how nth0 works. There's also a form that doesn't return the list. It has 2 forms, but that's the form we use. We take the operation that we want to do inside of the list, and then we use that to map the value to a new instance of the value. We call a function that is also not in this file. Which file is it in? I'll figure out what file it's in. I'll do that in a moment. We use that to map the new value again to a new value. And now we put the list right back together. So we are building the final version of the list. That's ln. We've built the value a2. We had lrem from here. As you can see, all the wires kind of connect up for some definition of connecting up. And you'll notice that this is, of course, the syntactic form used here, because there's exactly one item in the list. There's a second syntactic form used here by qadd and qzor, which, as you can see, I mean, all of these take two things, actually. There's A0 to A1. I've named these the same way. There's this extra auxiliary thing, which in the case of rotate is provided here as the argument to at here. But in the case of these other ones, we have to get the extra fancy auxiliary thing via a different way, which is this dual argument syntactic form. Anyway, what we do to get the other thing in this case is we take an additional index, where this is the index of B. The index of B is like the index that goes in this syntactic position that I'm highlighting now with my cursor, if you can see my cursor. We still take a function, or, well, a predicate that we call. Just remember function, predicate. Prolog will insist that they are not the same, because Prolog has decided that there's another word that function means, and as a result it will idiosyncratically use those words. I mentioned that there's another form of nth0. That is, of course, true. And, oh, didn't mean to put a little angle bracket there. That wouldn't have meant anything. So we're defining this in terms of the original one, and basically the difference that we're expressing that it has relative to the original one is that it has the exact same behavior, except that it gets B, which is the second thing, and then it defers back to this one. So effectively, it is the same as writing at D of qzor of whatever is in A. It is kind of like writing this. The difference being, of course, that A in this case is the index of the slot. This would actually be value in A or something like that. That's kind of what would be there, which maybe is useful to you. So this is actually the body of 2 rounds of Cha-Cha 20. It's called Cha-Cha 20 because it does 20 rounds. Might surprise you. So really all we have to do is define the entry point to all this logic, and that is to define the Cha-Cha primitive as doing 10 rounds, ultimately mapping B0 to B1. As a side note, you could also have just written this as, you could also write this like this. And some people might even prefer this. In fact, I might even prefer this. Neat little stack of 10 of those, huh? See, it's short. Is it good? Who can say, really? But it's short. Yeah. So beautiful. This is the implementation that we've got. Now, we do want to do one other thing just for cleanliness' sake, which is to say what function we export. This is to say what function from this module can be called by other modules. I also noticed that I've actually named the file in a different way that I might want. You'll notice that naming the file again convinces Visual Studio Code that this is Perl again, which it's not. It would be nice if it was. Perl is probably more suited to this problem than Prolog, which is really saying something. So there's one other thing I want to deal with before I deal with the missing definition of trunk 32, which definitely should exist, in my opinion. It's kind of weird that it doesn't. Yes, the other thing that I want to address specifically is that this is an extremely, extremely slow algorithm to do what it's doing. So we are actually building a new linked list. We're starting with a linked list that had 16 items in it. We're building a new linked list that has 15 items in it. We're doing one operation, then we're doing a second operation. These are constant time operations. They're fine. They're not slow. And then we're building a new linked list. So we're doing, again, this horrible operation on 16 elements. We also have this interesting case where operations on later indexes have different performance than operations on earlier indexes. Operations on earlier indexes don't have to rebuild the whole list. We only have to go as deep as it takes to get the node inside the list that we're changing. Whereas if I take the 15th slot, I have to traverse 14 pointers, or sorry, if I take index 15, that's the 16th slot, so I have to traverse 15 pointers. And then because I can't mutate a structure in Prolog, I have to build a new structure where the other 15 objects all now point at my new value for this slot. Or in this case, no value because I'm doing a remove operation, which is maybe not what we want. We might say that we would expect that to perform pretty badly, and it does. Prolog is extremely slow. Prolog programmers will insist that it's not, but I believe that it in fact is. I don't know. I've never benchmarked this program. This is a very new program. I just wrote it tonight. So we'll also add a file. This is just where we're going to put a variety of miscellaneous crap related to figuring out what type things are. I don't really need to use the word crap. I've already used the word goddamn in this video, and it's like nothing I say is probably going to be more intense than the word goddamn, which I've now said 3 times. I'm told that you're not supposed to use words like that on YouTube, though. I'm told that YouTube gets mad. So we're going to define 2 utility functions. I'm going to comment and include the C versions of these functions because they might help you a little bit in understanding what's going on here. Of course, we have to convince the editor there. That's good. Yeah, so this fittingly named function truncates a value to 8 bits. What it does is, we won't use C actually, we'll use Python. It's along the lines of if A less than 0, oh no, the program stops. And then we additionally say return A, and yeah, that's about right. So basically this will force the value into fitting into 8 bits in the most brutal way possible. This one does the exact same thing, which is to say it forces it into 32 bits in the most brutal way possible. Maybe that's what we want. Beautiful. Yes. There's one other horrible thing that we'll write. Actually, there might be 2 if we're if we're lucky. So this is going to be a function that turns an array of U8s into an array of U32s in little endian representation. And because it's a predicate and it doesn't use anything that is obtrusively directional, it can actually be called in both directions, which is of course one of the main features of Prolog, which is that you can write predicates which can be called in both directions. You'll quickly see how that looks. So we haven't written this as int function yet. We'll do it in a moment. But we're going to say that if ABCD, which is the name of a variable, can be represented in 4 little endian bytes as A, B, C, D, then that's good. Please do that thing. Having it up here means that the variable that was passed to this function will be populated with this, or more broadly, that the value that was passed to this function will be unified with this value that we have here. And yes, this is a recursive function. We want to keep calling it. As a side note, you'll notice that if this is called with anything that doesn't match these patterns, it will fail, which is to say it will stop producing results. And Prolog will see this as having returned 0 results, which will generally stop the program. That's not true. It will cause another clause of an earlier function to be tried. At any rate, yeah, this will not produce a result if it's called with a number that isn't divisible by 4, which is generally desirable for this kind of thing because we kind of know what size all of the arrays in this program are. Yeah, I think that's pretty cool. We'll do it like that. Oh, we'll add one other thing, and then we'll do asint. One of the things we can do in Prolog is we can create a list just by saying what its length should be. The length function will do the right thing if you call it with a number and an empty variable, which is to say it will put a list into that empty variable that has that length. Map list takes a predicate and it runs that predicate for every element of the list. And right now this is a list of variables. So this is effectively, if we say that that n is 3, we'll say that the list now has x, y, z in it. It has length 3. So this will apply equals 0 to x, equals 0 to y, and equals 0 to z. And that results in a list that looks like this. And that's useful. Maybe it's useful. We'll find a use for it. I know that we'll find a use for it because I remember writing this function. I remember why I did it. So we also have, by the way, the need to transform integers into different representations of those integers. We, of course, are calling as int le. You'll notice the fancy for here. We'll use the word width to describe the number of bytes wide that the integer needs to be. We'll say, actually, we should do the base case first. So we'll say that if our integer has a remaining width of 0, then it is representable as 0 bytes and its value is 0. That is a true statement. 0 at length width 0 has this representation. We'll additionally say that if the width is something other than 0, that is something greater than 0, excuse me. We won't have a case for less than 0 because you can't represent an integer in negative number of bytes. We'll say that, so we have this value v1. We'll say that, yeah, the width has to be greater than 0 for this case to make any sense. We will then say we need to calculate the width of the rest of the bytes is what we have to do, which makes my code a lot more confusing. We'll additionally say that, this first byte has to be a concrete value. We're gonna have two cases for this. This is the case where, sorry, I should back up and explain my approach, but I think instead what I'll do is I'll write a little bit more code so I can kind of gesture at the code while I explain my approach. I think that would be actually more effective. I think this is one where it helps to see the shape of the program more than it helps to be directly told how the program works. Okay, so basically there's two ways that this function can behave. One is that we can be passing it a list of bytes that are known, but we don't actually know what this value is, the value that the bytes represent. The other option, which is equally exciting, is that we know what the, so this recursion is the same either way. We know what the value is. We do not actually know what the byte representation is. You'll notice that, technically speaking, these cases will still trigger if we know what both of them are. It's just that all it will do is return true if the bytes are a good representation of the value. It doesn't do anything especially interesting, but it does work. So we can also compute the byte representation from the integer, which would look something like this. Right, and hopefully I haven't done anything too horrible here. Yes. These are functions that convert between lists of integers that are wider than 1 byte and integers that are just 1 byte. We primarily will be operating on integers that have a width of 1 or 4, at least for the first part of this. We'll be doing some more interesting stuff afterwards. So yes, we now have these representations. We now have the cha-cha 20 primitive, which is to do 10 double rounds of cha-cha, which looks exactly like that, which maybe we find that to be useful later. So I think that the next thing that we have to do is we have to actually implement cha-cha, the cryptographic. We have to implement cha-cha, the cipher, and while we're at it, we have to implement the cha-cha initialization logic, which we'll do. So I've mentioned that this is a crypto system, and all we have is a function that maps 64 bytes to 64 bytes, which might be useful if your goal is to map, oh god, not Python, no. Oh, it's starting my Python tools. I don't need them. This is obviously not a very useful algorithm if your goal isn't to map 64 bytes to an arbitrary 64 bytes, which probably that is true of you. So there's two exports of cha-cha we'll go with. One is the function that we've just seen, but with a particular set of initialization logic. The other export is a cipher, and we'll go through both of those. We'll start with the one that's much less remote from what we just saw. Effectively, we take a key, a nonce, a counter, and we produce a state and a mixed version of that state. We have two versions of the state that callers can choose from. Now, we have to do a little bit of basic hygiene stuff. The key that we accept is a list of U8s. You've probably repeatedly heard me say that we have 64 bytes, which represent 16 numbers. The key is, of course, by default, it's a series of bytes, because that's how we represent things usually when we can get away with it in the public interfaces of crypto. But it's going to be turned into exactly 8 U32s, which we have those U32s. There's actually some disagreement over whether the counter should be represented as 2 U32s, or whether we should have 1 U32 and then some kind of other information that represents the state of the encryption system. I would say that I personally, for the algorithm we're implementing, favor 2 U32s, which mildly differs with the specification, but not in such a significant way that you can't bash it into still accepting the same test data for the purpose of figuring out if your implementation is accurate. So we also want to turn the nonce value, which nonce in the case of a program like this means number used only once. We want to expand that to this 64 bits or 8 bytes or 2 U32s of data. Beautiful. So we've taken all these values represented only in bytes, and we've re-represented them as U32s, which are, of course, the only thing that cha-cha uses. So this is going to involve minor copy-paste. This set of strings may look mysterious. This actually is equivalent to the following string represented in the most natural way for little endian processors. Like, if you were to take this exact string and just cast it in C to an array of U32s, this is probably how your computer would interpret that. These are the initialization constant of this algorithm. The reason that this constant is used is basically because it is an arbitrary value that clearly was not chosen because it has some non-obvious property that the creator of the algorithm, crap, is it Daniel Bernstein or David Bernstein? I'm pretty sure it's Daniel, but if it's David, he can sue me. Yeah, the idea is that if he were evil, he might have picked a set of values that make the algorithm breakable, in some case known only to him. He has not done that. He's picked a very obvious value that anybody could have come up with. So we then initialize the other fields. This is the 16 elements of the block that we were talking about. Might have even been better to start here, actually, because, like, you know, now you can see one. Now you understand what it looks like. So we've built this up, and it contains all these constants that the algorithm starts with. You'll notice that 75% of these come from the caller, which is kind of a lot, but hey, it's not all of them. One of the design goals of this algorithm is that the caller shouldn't be able to determine what all of the values in the block are, because they might use the extra values to force the function that we just wrote here to, say, repeatedly return to the same state, which would be useful to somebody who wants to get access to the message that was sent, because they wouldn't have to try as many things. They would be able to see that parts of the message are identical to other parts of the message in some way. So, okay, we've built that out. We then actually just call this function that we already wrote. And what do we call it with? We call it with, that's right. And that'll get us the state. So it'll be more obvious why we have a mixed state output once I show how that's actually defined. This is the result of calling dround a bunch of times, which is a very scrambled instance of the matrix that we have. So I'm going to define one more function, and then I'm going to make it obvious why we have mixed state. Right. So we're going to do one other thing. We've started with this initial state of the matrix. We've then made another state of the matrix here. The operations involved in the algorithm we have here are all reversible, which is to say that in principle it is possible to get back the original state of the matrix by running this algorithm backwards, which is maybe not desirable because if we want a really garbled matrix, we want it to be effectively random what matrix we got out. I should actually clarify, first of all, why it's desirable for these to be reversible. Effectively, if these operations are reversible, we can feel a level of confidence that information is not being lost as this continues. Like, let's say that this algorithm had the effect of reducing the number of ones relative to the number of zeros twice as fast. It got rid of ones twice as fast as it got rid of, or sorry, it was twice as likely to turn a 1 into a 0 than to turn a 0 into a 1. We'd kind of expect that to eventually result in a matrix that has all zeros in it. So the idea is that there's exactly one place where cha-cha 20 loses information, which is this mixing step, which adds the original state to the finalized state. And this step can't be reversed as easily. I should mention that you probably should take my crypto opinions with a grain of salt because I'm not a cryptographer. I'm just a hobbyist. And cryptography is easy to get wrong in subtle ways. This program actually has contained, no doubt, several mistakes beyond the ones that I've pointed out that most people would find worrying if they were literate about cryptography enough to be worried about it. At any rate, so we add all of the elements of this original start matrix to the scrambled version of the start matrix, with the expectation that this very scrambled version will, yes, this one is not, it's not possible to easily deduce the original state from this without having access to the original state. Very cool. All of this to say, we now have our scrambled, we now have an effectively random value. We have a random value that has incorporated the information in the key nonce encounter such that if I were to change one bit in any of these, I'd probably get a completely different random value, which is maybe useful for our purposes. We'll now write the the cha-cha 20 cipher, which actually uses this exact function to encrypt a string, and then it will become more obvious like why it's useful to have 64 random bytes. To spoil it, the reason it's useful is because if you can have 64 random bytes and you have a value that you can just repeatedly raise, you can have as many random bytes as you want, and having a bunch of random bytes means that you can do a one-time, you can do the same algorithm as a one-time pad, except that instead of having to memorize the entirety of a one-time pad, you just have to remember these. This is basically how stream ciphers are usually constructed, is that they have a reversible operation like the XOR operation in the pad, and then they have a source of random data. That's how you would normally do it. Sorry, this is me tangenting horribly because I've actually got to show you how the thing works, or else you're not going to have any idea how the thing works. So we've got a key nonce counter, the plain text, we'll call it plain text, and we've got the result. Very cool. We'll, yeah, we'll start by, oh god, I got another function to write, huh? I'll come back to this function in a moment. If I do everything at a leisurely pace like this, I'm never going to get anywhere. You know, actually, I would say that the right word would be input text. The reason being is that this is also actually the function to decrypt cha-cha 20. They're the same function because, of course, they are. It's a reversible operation. And yes, we probably should recurse. Right. Okay. So we're going to increment the counter, and then we're going to go right back and call the exact same function. We will ultimately produce a giant pile that contains all the output text. One of the many reasons that Prolog is, well, this isn't really Prolog's fault. This is a very inefficient way to build all the output because it's a recursive function that returns. That is, this isn't a tail call. There's code to return to after it's done here. And the effect is that the more text you have, the more space this will waste. And also, because this is using append in the standard way, this is actually a quadratic way to build the full output text, which is to say it's not a good way to do it. Of course, in most languages, you'd use a string builder. In Prolog, you'd actually use you'd use the tool I showed you earlier, the DCGs. You'd build what's called a difference list, which is to say that you'd repeatedly have the caller pass a variable that hasn't been filled in yet, and that variable would be the last node in a linked list. And it's a very cool technique that, unfortunately, I'm not going to show off in this video because I haven't prepared it, and it's complicated. So the key stream is the thing that we mix the input with to get the encrypted version. And I've mentioned the key nonce encounter repeatedly. You can just for now think of all of these as effectively part of the key. Later it'll be clear why they're different, but right now they're honestly not. They're just all part of the initialization for this cha-cha-20 block feature, which wraps our primitive from earlier. So for the key stream, we use the non-reversible version. There's exactly one case where we use the reversible version, and I actually don't understand the cryptographic reason for it. I think that it doesn't make sense to me, but hey, we have to. If it were up to me, we'd always use the mixed version whenever we need any output from this, but perhaps people know things that I don't know. Yes, so anyway, we compute the key stream, of course, because we need it. We'll now write a function that mixes the key stream with the plain text, which produces the ciphertext, or the exact opposite. It takes the input text and turns it into the output text. As a side note, this can also be done with maplist, which is a reasonable way to do it. I think it can at least. I actually don't know how you deal with the fact that the key stream is longer than the input stream. It might be handled by maplist. I can never remember how that works. I don't use Prolog enough to know that. So we can look at this now. We have basically a correct implementation of cha-cha-20, the basic cipher now. Unfortunately, this isn't the end of the video because we have a few other things we need. So we can talk a little bit about the pragmatics of using cha-cha-20. We're going to fill in our entry point a little bit, and I'll talk a little bit about how we actually have to use it, which is important because while we have this primitive, we don't have anything to call it with. We haven't given it anything to initialize with. So this is just a little bit of boilerplate code to handle command line args and stuff like that. Yeah. By the way, these look exactly like TypeScript type annotations. I promise you they're not. This is actually how you take a dictionary, like what we would use to represent JSON, which we'll do later, and get a value out of it. So key in uppercase will be set to the value associated with key in lowercase from the dictionary, which is a little bit backwards from how you'd expect this to work. Really, the important thing to get here is that nothing here is a type. So we have this stub. We'll have a similar stub which applies to decrypt. I already have it lying around, fortunately. Right, so the actual goal is going to be to produce something that decrypt can consume. Now, I mentioned the concept of a number used once. If we were actually doing this completely 100% from scratch, we would provide a source of RNG. One of the better RNG algorithms in practical use is actually cha-cha-20, the block function here. Effectively, you start it from a state that you believe is highly random. You just increment the counter repeatedly. It's exactly the same as what cha-cha-20 cipher is doing with this key stream, except that you don't mix it with input. You just produce the key stream. This is not by itself a solution to the problem of random numbers, because if you're starting it from a known state, then all your random numbers are known, your nonce that you generate is known. There's two solutions to this that I'm aware of. One is to generate the nonce as the cryptographic hash of some other value, which is to say you pass the value to a fancy mixing function, sort of like this one, except, well, not reversible, so more like, or yeah, like this one, and not like this one, which is reversible. You pass it to a funny mixing function, and then you use that to generate the key that you need. Actually, shit, no, they don't use that to generate keys. That would be, or sorry, nonces. That's what I mean. Yeah, you can generate a key from randomness, but like it's important that keys have properties that are important that are different from the properties that are important for a nonce. I'll explain in a little bit why it is that it's important that a nonce genuinely be used only once, and that'll make it more obvious what compromises you're making if you use a digest a hash function to populate it. The other thing you do is you have an OS level or even a hardware level RNG, and that means that your nonce is probably genuinely random. You'll notice that I said that 24 is a pretty good size. You'll also notice that's not the size that Cha-Cha uses. Cha-Cha uses 8 bytes because it has a nonce that is 2 U32s. 2 U32s is probably too small for a lot of use cases, which is one of the reasons why people argue about whether the counter should be 1 U32 or 2 32s when it comes to this here. A lot of people argue about whether one of these should be moved to the other ones. There's a much better solution to that problem that we'll get to, and it's the reason why this can be 24 bytes, which would be 6 U32s. It would be this many U32s, which is a lot of U32s. Anyway, we've got a lot of horrible crap to write, which fortunately I already have, so I'm just going to copy paste it in, and we'll notice a few other things that spoil where this video is going. This is, of course, clearly not the function that we wrote, and what is all this shit? It's just boilerplate to turn strings into bytes and hex values into bytes and all that other good stuff. And likewise, we're going to have a decrypting function, which is the reverse of this. It calls the counterpart function to this. Beautiful. So what you should take this to mean is that our actual practical inputs are associated data, a message, a key, and a number used only once. Some people will break this down into a few more. There's frequently an implementation constant that travels with the nonce, but it's morally a part of the nonce when it comes to how it's actually used in the algorithm. Basically, we're just stealing one of those. We're stealing a uint 32 either from the counter or from the nonce to store some constant information, which is a thing that we're allowed to do. Anyway, I'm going to move on from the cipher, which we've now built, and it probably works, to the next thing that we're going to solve as part of the problem. So the problem with this approach is that while people might not actually know what our message is, they do know that our message is the XOR of a random value with they do know that our ciphertext is the XOR of a random value with the message, meaning that our adversary can still flip a bit in our message just by flipping a bit in the ciphertext. Effectively, I'll use English for this. Let's say that our message is hello, and our key stream is we'll give it a better key stream. We'll go A, B, C, D, E. So the effect of this might be that our message becomes, I don't know, there. So that's the same number of letters. It's the same amount of everything. So our adversary sees this message, IJMME. Very cool. I guess I should actually, I can make this more random. Cool. There's not necessarily any association between the characters in the original message and the transmitted message. So we've got this ZJMPE message. So our adversary sees this and wants to fuck up our message. Oh, I said a worse word than goddamn. So they replace the J with a K. And they, by doing this, despite not knowing our message, they do change the decrypted version in a predictable way. It becomes, for instance, HDLLO instead, which is really bad. It could also, I don't know, it could become HFLLO. So we want to prevent this by detecting accurately when the adversary has changed something about our message. So what we use is something called an authentication system. So for this draft, because I'm implementing the scheme with the extremely long name that I can't easily repeat because words are difficult for me, because we're using that scheme, we're going to be, using the function that that scheme uses. So poly1305 is a pretty easy algorithm to understand, except when I'm explaining it, then it's very difficult to understand. The gist of it is that it takes a key, which we are proving it takes a key, some text, and a tag, and what the tag signifies is that somebody who knew the key saw the text. The assumption is that only the person who is actually sending the message would know the key for this message, or the person who is intended to be receiving the message who is checking the key. So the key has some structure. The key is emphatically, it is a random value, but it has some structure in the sense that we're going to zero out parts of that value, and we're going to split it into two values after we've done so. So the operands of poly1305 are very large numbers. They're numbers between 0 and 2 to the 130. And the nice thing about Prolog is that integers in Prolog don't have a fixed size, meaning that the entire algorithm becomes very, very trivial. That is to write code for. The downside is that Prolog's math is implemented in a way that means that the amount of time that each operation takes is very heavily affected by what value you put into it. And the reason that's really bad is because somebody who isn't supposed to know anything about these values might be able to deduce something about what these values are based on how long it takes you to do the math. For instance, if Prolog is smart and it can actually, we don't need to include assertions. I already know the code is correct because I wrote it once already. Or wait, these aren't assertions. What am I talking about? Yeah, but anyway, like if the adversary can figure out that one of these values is 0 because Prolog returns instantly when it sees a 0, that adversary could reverse engineer what the input was to produce a value of 0, which is probably really bad because the security guarantee goes out the window. Usually this would be represented, there's a really good article on the blog of Loop Valent, who wrote Monocipher, which is the cryptographic library that I referenced heavily while making this, explaining how you can do all of this math using 5 integer variables in C and only operations that take a constant amount of time. This last line is going to scare you, but you don't have to be scared of it. The gist is that we're zeroing out parts of this strategically such that the multiplication can be done slightly faster in C. And the exact bit hacks used to do that, I don't really understand. But if we want to comply with other implementations of poly1305, we have to zero out the same parts that they do. So the constant that poly105 uses is this value. When I said that the numbers were in the range of 0 to 2 to the 130, this is what I meant. And again, I'm going to go ahead a little bit and then I'll attempt to explain what's going on to the best of my ability. I guess to start with, we've divided it into these two parts, R and pad. We have a value that accumulates, and I'll show you in the form of an arithmetic expression what's being accumulated, but first I need to actually write the final step. This is the base case of the algorithm. So the gist of what we're doing is for every fragment of the message, let's say that our message can be understood as chunk 1, chunk 2, chunk 3. We have an expression. Initially our accumulator is 0. We see chunk 1. Accumulator is equal to accumulator plus chunk 1 times R. That's part of our secret. We see chunk 2. It's equal to chunk 2 times, or we add chunk 2 and multiply everything by R again. That's still part of our secret. We do this for every chunk of the message, and then we finally add P, the other part of our key. So every chunk of the message will affect accumulator by it has the potential to affect any part of the accumulator by any amount, but the exact amount is only known by the person who generated the key. The rest is a mystery. And then, of course, after the entire message is through, we shuffle it by an amount only known by the person who has the key. There is some kind of proof that shows that this doesn't leak any information about the message, and I do not understand the proof. I do not know anything about it. I am not a cryptographer. Thank you, Visual Studio Code, for wasting my time with the dialog box. Effectively, what I can tell you is that this is believed to be a pretty good message authentication code, and if all that you can say about it is the stuff that I have just said, then you should not be writing cryptographic code. Anyway, I'm going to keep writing cryptographic code now. So we load our constant. We still have this function that I've yet to adequately explain, but basically it, despite being named append, it removes the chunk of a given length from the beginning of a list if the list is longer than that length, and otherwise takes what remains in the list. So this will get up to about 16 bytes. From text. We'll actually go with a slightly better naming convention. We'll go with text prefix, text remaining. Yes. There's one other thing this algorithm does, which is this. The gist is that this algorithm is trying very hard to be sensitive to the length of strings. It doesn't want to produce the same result for... so it chunks your string into nice little chunks of 16 bytes. So you might have a string that looks like this. And you might similarly have a string that looks like this. These would be interpreted into the values. That is, if we do nothing, this one would be interpreted into this value. And this one would be interpreted into this value. And they're the same value. So there would be no way to distinguish authentication codes, which are this tag that witnesses that a person who has this key saw text. There would be no way to distinguish between the codes generated as a result of this because the chunk of the message that we use is the exact same. So what we actually do is we add an extra byte that looks like this to the end of every message. So I'll show you what that would do to the codes. Right. So now if we line them up, we can see they're different now. So basically we're going through chunks of 16 bytes plus 1 bit, which will fit in the range of 0 to 2 to 130, despite the fact that we've got this extra bit, which is fantastic. That's exactly what we would like to do, and now we can distinguish the length using these chunks. And let's see, we'll take the actual length of the chunk. Right, so you saw previously the arithmetic expression that I wrote. We're going to build a new version of the accumulator as oh, yes, we do have the prime. I had lost the prime. I'm very clumsy. Yes, then we just call back into our existing code, which I should name correctly. I'll fix that call in a moment. Don't use Prolog, by the way. It's terribly verbose. There are problems that it's good for. This isn't one of them. I hesitate to say that, actually. Prolog has some of the worst error reporting I've ever seen in a programming language, and it's possible that if I were better at it, I wouldn't say that, but that's my general experience, and that made this program pretty painful to write. So we now have this implementation of the Poly 1305 message coding, or sorry, authentication coding system, which means that we can figure out if a person who had this key saw this text. We haven't wired that up to anything, like where does the key come from, where does the text come from. It's a total mystery. I say that, I know it's not a mystery because I wrote the rest of the program, but you haven't seen the rest of the program, so it's not very helpful to you. We'll also, because we're going to need to use a function from that anyway, we never actually... It'd be good to do this because then we'd be able to, yes, use this externally. technically it'll let you load the module anyway, even if it doesn't have this declaration. It would just dump all of the functions defined in the module into your scope, even if maybe that's not what you want. It almost certainly isn't what you want. Cool. So let's see. We've got one other function to throw in there. It's that append chunk function that I mentioned earlier, which fortunately I still have lying around somewhere. Yeah, this one is on the complicated side, but it's not significantly more complicated than asint le. There's actually two ways to write this, and I'm tempted to do it the simpler way. But no, I think I'll do it the way I did because I'm more confident in its correctness. So the gist of it, remaining will actually explicitly say, no, we won't explicitly say that remaining has to be non-empty because it's fine to take a chunk from this otherwise non-empty list. Right, so we can either take a chunk of size or we can take a chunk of less than size only if there is nothing left. We do have to actually take something. We'll handily die if there's nothing to take. We also will not simply take the entire thing, which, to be clear, would otherwise happen when Prolog recurses to the second case. There's, by the way, a between function, or sorry, a between predicate that can also be used to write this kind of expression. I just kind of prefer this. So we should be good on that. We've now got our authentication code system. We now have to actually tie that to the code that we've already written, which is over here. I've got that file right here, and I'll copy out of it diligently and usefully. Right, we've got to convince our computer that it's not Perl. Beautiful. If it was Perl, I'd tell you. And we won't export our functions yet because we don't actually have any functions. Right, so there's a standard way of connecting cha-cha-20 to poly1305. You can look up RFC 8439 if you want to see it. I believe it was a rejected RFC, but that didn't stop a bunch of mobile phone vendors and similar from using this scheme. And you can still find it in libraries like libsodium. Actually, libsodium, which is this very popular cryptographic library that I'm not using, will actually use the scheme that I ultimately implement, which is a derivative of this scheme. So we take the AAD, which I keep dancing around the question of what that is. I'll explain it in a little bit, or maybe I won't. I haven't decided yet. You'll notice that I have this whole counter offset variable that is there as part of a hack to comply with how the standard defines how we argue over this extra bit, or sorry, this extra uint32 value that I keep complaining about. There was a period when we could only use nonces that are of this size before people came up with the hack that I'm about to use that allows for much larger nonces. There was a period when fighting over this extra uint really, really mattered. It doesn't really matter now. Well, maybe it does, and I'm uninformed. I don't think it matters now. So anyway, we will be doing a few things. One is that we actually need a key for the algorithm we just implemented, poly1305. Now, I haven't written the code to generate that key yet, but I will soon. The other thing we have to do is set the initial value of the counter. So, well, we have to be able to spell counter offset. If we can't do that, we can't do anything else. This, by the way, could still be written. Yeah. Just as a note. Yeah. That helps me remember that in case I apparently somehow managed to forget that. As a side note, the non-boundedness of the integer types in Prolog is another reason to not write cryptographic code in it. It's really not a good idea, and it means, for one thing, non-bounded integers inherently leak information about how large they are, because if your integer is 1,000 times as large, it will take 1,000 times as much time to process. If it's bounded, you can control for that by always using the big representation. But if it's unbounded, your computer doesn't have unbounded memory, so you can't. Anyway, we'll call into the cipher that we already wrote. Now we have a value, and as you remember, poly1305 gives us a witness that a person who had the key saw the value. So this is the only place where the AAD is actually used, which is in generating the value that we are creating a witness that we saw. So now I can cleanly say this. The AAD is some extra data that we are witnessing that we saw, or sorry, that the signer, not the signer, the authenticating party is witnessing that they saw. Meaning that, let's say that I have a message like this. Right, so okay, so we're going to encrypt this and it becomes Pyrex, Kobold, Cool, IM. This is a really subtle cryptographic algorithm. It's on the level of Pig Latin. So anyway, this is actually, I'll make it more obvious that this is encrypted. And I'll put it in fancy brackets that I guess signify encryption. Right. So there are two options for what we could have the person sign. One of them is that we could just have them sign the encrypted message. And if that were the case, then we would be able to distinguish right. So we might see this message instead. If the only thing that we have signed is this block of the message, we'll represent that like that. Right. Again, I'll use the word tagged or authenticated there. We'll use that word. If it's not obvious, I'm absolutely petrified that a cryptographer will find this and just skewer me for not getting things right. That's basically inevitable. Yeah, so, yeah, if that's the case, detected as fake is inevitable. The problem is that there might be a message that looks like this. Now, it's entirely possible that Bin would say such a thing. And in practice, in the world where Pyrex and Bin would be using different cryptographic values anyway, this difference might not matter as much because, for instance, let's say that Bin has a different key than me anyway, then the message authenticated as being from Bin could not be attributed to me because the key wouldn't be right. However, in systems like, let's say that you're running an encrypted chat service or something like this. Well, for one, you shouldn't use this algorithm for an encrypted chat service. You should use something that provides end-to-end encryption, which this doesn't. But if you were to use this algorithm for an encrypted chat service, then all of the messages would be authenticated as being seen by the same party, which is whatever code has authority to encrypt and decrypt things. And in that case, Pyrex and Bin's messages would actually hold the same signature, or they would have the same signing party, which might not necessarily mean the same key, but it might mean that it might mean the same key is at least plausible for both. So the AAD, oh, I should actually clarify. Let's say that we take this exact message. I'll complete the explanation. Let's say that we authenticate with, or we create a MAC for this. In that world, yes, the IAD, which in this case is Pyrex, does not match. So Bin's message is detected as coming from, well, not Bin. It doesn't tell you who it originally came from. And the evil hacker who is impersonating Bin would be outed as having done so. All of this to say, AAD is useful in certain scenarios, and in many other scenarios it would just be 0, but it's kind of nice to have it as a feature. So, oh, I should actually use the word encrypt here because we're going to have a decryption function in a little bit. So we've now generated a tag. We've also generated the enciphered value. One other thing you'll notice, by the way, is that this, in theory, could be secure if we created the MAC over the plaintext. However, there's really no reason to ever do that. Like, I can't guarantee that it would lead to your destruction, but like the only thing that we're witnessing is that somebody with the key saw the ciphertext, and you really don't want to do anything that has the potential to leak information about the plain text, even if you're really sure it doesn't. So like your authentication scheme just is able to work while knowing absolutely nothing about the plain text, and that's a nice property that we should try to keep if possible. That is not just me sandboxing. The Signal guys have written several blog posts about this where they call the rule that I've just described the cryptographic doom principle, presumably because you are doomed if you violate the rule of always checking authentication first and discarding if it doesn't pass. Anyway, at this point, because you've been paying attention, you could probably write this procedure by yourself, or maybe not, because Prolog's like that. We've got this function that decrypts. We're going to keep the algorithm almost the same, except for the fact that except for the fact that we deliberately crash out if the tag doesn't match instead of outputting the tag. So we have here this expected tag. Incidentally, in Prolog, you could also do this if you wanted a less violent crash. This would just make your program print the word no and then exit, which is the default way that Prolog handles errors. This is a much more violent exit. I say that's the default way that Prolog handles errors. There's some nuance to why it's like that. The gist is that Prolog backtracks and retries, and that's how functions can return multiple values, how you can have one value that appears to be the return value in one case and appears to be the argument in another case. It is central to the coolest features of Prolog that Prolog handles error scenarios by going back and retrying, and it is a result of how it goes back and retries that if it runs out of things to try, it just says no and ends your program, which is just this very useless behavior. So we represent the MAC data by padding everything to 16-byte increments, but also keeping the original length around so that we're not like, so that we can distinguish if the authentication data got longer or shorter. Or sorry, not the authentication data, the associated data, the unencrypted data got longer or shorter. I think that covers everything here. We represent the lengths as 8-byte values. The amount of space this uses is not important because this is just the input to the MAC function, which is similar to a hashing function. It's not actually, there's like the MAC function, if you know all of the values, it is possible to deliberately create messages that would have the same MAC value. Like you can just reverse engineer it because the algebra is incredibly simple. You can figure out, like, for instance, given a certain R value, you can find a value such that the result of this expression is going to be the same as the result would have been with a different block value, and that's not terribly difficult to do. So that's, if somebody is evil, they can come up with an authentication code that would apply to multiple messages, and that's not true with other authentication schemes like HMAC, which was what I was originally going to do for this video, but it seemed like I wanted to do cube hash because cube hash is a really funny algorithm, but I didn't get around to it, and this is much simpler anyway. So, okay, we'll finish off with, like, we actually do need to include our padding function. We don't have it. I mentioned that we'd be generating a key and that it would be using cha-cha-20. Fortunately, I do have the code right here. We can see here that we just take a block of cha-cha-20's output, specifically the mixed version. We just take the first 32 bytes off of that, and then we use that. This is the same idiom where we create a list of length 32 by using the length function, then fill it in this case using the prefix function. The append function, which you've also seen in the program many times, would also work here. Beautiful. And again, you can just imagine that I've said the word predicate every time that I didn't say the word predicate. So we're getting really close to having something working now. Unfortunately, this next step is not a small amount of code. The gist of it, and I've been hinting at this for quite a while, which might distress, oh, actually, I'm gonna hint at it a little bit more in a moment, but first I should just export these functions so that everybody else in the program can see them, because that'd be pretty cool, right? That's not even the name of the function. Beautiful. Okay, that's, well, maybe it's beautiful. Depends on your definition of beauty. Right. So we've got one more thing to expose. You'll notice that there's an X before the word cha-cha. I don't know what the X stands for. I assume it stands for excellence. It might stand for something else. This is another RFC that got rejected, presumably by the same people who rejected the previous one because they didn't like either, or possibly just because time ran out. So we've got here a wrapper that allows for a nonce that is longer. This nonce is actually 6 bytes, and I'll show you where the 6 bytes go in a moment. We will, of course, have a skeleton that just calls into cha-cha-20, which is the function that we just defined. This, of course, calls into it with n1, which is this mysterious value. There's this separate value, n0, that is produced by split nonce and dumped into hcha-cha-20, and we just don't know what it is. What we do know is that the decrypt and encrypt algorithms, in order to produce the same, if we assume that cha-cha-20 poly 1305 is a good cryptographic algorithm, which we generally should because Google does, they use it in Android and other people do. I keep mentioning Android. I'm sure it's used outside of Android. I just specifically remember reading that it was used in Android, and I thought, oh, neat, Android is cool. And then I read about other algorithms that used to be used in Android, and apparently there was this horrible one from the NSA that they used for a while, and that's like what this thing is replacing, and that's like, well, that's scary. I don't know if I trust the NSA with my computer. Or was it the NSA? I don't know. This is where I become very paranoid, and there's really nothing to do about it. Regardless, the steps of these are effectively the same. The flow of data is actually in the opposite direction in this case. That is, the flow of data is from ciphertext and tag to text. But we've defined these functions as having almost the same signature, so our code happens to look basically identical. The steps are roughly the same. So we've split up our nonce. We have 16 bytes that go to this hcha-cha function, which who even knows what that does? I do because I wrote it, but and also because I read the spec. And then the normal 2-byte nonce goes to, the normal 2-byte nonce goes to the cha-cha-20 function. This is basically a prelude to cha-cha-20 that does some extra initialization that might be desirable. So hcha-cha-20 is going to look a lot like a function that we already wrote. In fact, there's really only one way that it differs from the cha-cha block function, and you'll see it pretty soon. Right. Oh, I'm sorry. I forgot to call the implementation. I'm copy-pasting today, and I'm doing so very sloppily. It's pretty late. That's probably part of it. I should probably get some sleep. So we have the implementation. The implementation uses this mysterious hcha-cha-20 block function. It initializes it in a way that we'll see shortly. We haven't seen it yet. So this is extremely close to the initialization that we saw in cha-cha-20.pl. You can see that here. It's almost the same, except that we have gotten rid of all the fighting over which bits go to counter and which bits go to nonce. We just take all 4 of these U32s and we dedicate them to the first part of this nonce. Now, you'll remember that the primitive, which I assigned a different name in this case, what did I name it? I just named it prem. Yeah, the primitive here produces a value that is a reversibly scrambled version of the input, which is part of why I'm confused as to why we use it as a subkey, but it makes the test vectors pass, so I assume that there must be a good reason. We produce that, then we use exactly 8 of these U32s as the totally random, not actually random value that is the key for the rest. So effectively, we've generated a new random key using an RNG that was seeded from the old key. This is presumably fine because the old key, it's not like we've lost information from the key or anything. It's like the key still had however many bits, I guess 256 bits of entropy, and we're in a state that we've effectively taken a random permutation of a block large enough that it would, that if you, we've permuted 512 bits, and we've taken 256 of those bits. And because it is a true permutation, or is it a true permutation? Shit, I don't know. What I'm badly explaining here, because I don't fully understand it myself, is that it is apparently fine to reseed from a bunch of random bits taken from the RNG that was created with this key. We expect the reseeding to still be fine. And if you can tell me why, be my guest, but it's a bit of a mystery to me too. Which is a pity because this is supposed to be very cool. This is supposed to be cool that we're allowed to do this. At any rate, we now have a different way of initializing cha-cha-20 poly 1305, which might be useful to us. What remains is, one, to work out all the bugs that I've inadvertently introduced by copy-pasting badly, and two, to actually run the program. So I mentioned we've got our key. Again, this really isn't how you're supposed to create a key. It's bad to do this. Seriously, just generate it using any random key generation method. We have this message. We can actually make this more similar to our example. We can say that our AAD here is Pyrex, which is, of course, my name. We can badly use the computer there. Wow, my mouse is, I'm not as good with it as I thought. So we run our program here. We should actually start it in a way that invokes the fancy command line flags we have here. We'll do it like this, and then we'll make some changes to the script as we demonstrate it. And if it works first try, I'll eat my hat. Oh, that's the stuff we want to see. That is, of course, how Prolog fails when it fails. It's interesting that it failed that way, actually. Oh, it failed because absolutely no match exists in main because we didn't write an entry point. Right, well, here's a bunch of garbage that'll be mostly self-explanatory, but not especially pleasurable to read. We'll find the processor using the processor predicate that we wrote. We'll read some JSON files. I'll include the function for that later. These exclamation points basically mean, hey, you found the right solution. Please don't try another one. They're useful in more imperative code to make sure Prolog knows that it should not try another code path. Although I've been told that you should never use these for correctness, I don't know what you do use for correctness. This is, of course, just some generic file I/O. Does it work now? Oh, God, no, it doesn't work at all. Well, of course, we didn't throw in the JSON library, and we haven't actually imported anything. There's one thing. Actually, we only directly call that thing, so let's just try that. Oh yeah, there's the good shit. What is broken? Oh God, am I calling that function? Yes, I am. Well, okay, I didn't include that function in this version of the program. So in the original version of this, I had like all this validation and stuff, but like writing validation in Prolog, just assume that like there's twice to 3 times as much code here just validating that it went to the right state, because Prolog's error handling features are so good. There we are. Now, what else is broken? Well, that seems horrible. X-cha-cha poly 1305 doesn't oh. What a stinker. Look at that. We're going to just keep seeing these for the record. We're probably going to have like, we could have like 10 to 20 minutes of this if I'm lucky. I'm not going to cut any of this either. I don't edit my things. There we are. Now, singleton variable. Let's see what that means. What it means in this case is that we referred to it as byte at one point and b at another point. A singleton variable is always going to be empty when it's used because nothing is put in there. And once you put a thing in there, nothing's going to use the thing that you put in there because it's only referred to once, and that's bad, huh? Oh, AO. Nice touch. I'm glad I'm in a font that makes that clear. We have... Oh, okay, well, wait. Trunk 8 is not defined? That's horrifying because I'm pretty sure it is. Yeah, it's right there. Come on. Oh. What a doofus. We've got a lot of other things to export too, don't we? I guess I'm glad that it makes me do this at least, because otherwise I'd just have like total chaos in my global namespace. Oh, operator expected? Did I? Oh, I forgot a comma. That'll happen, won't it? Ciphertext.json doesn't exist. Oh, yeah, I know why that happened, because it didn't finish the first time. Singleton text prefix. Oh no, what did I call it? Did I call it something else? I probably did, didn't I? Okay, so let's see. Yeah, I called it bytes, which is incredibly descriptive. Did I do that more than once? I better not have done that more than once. That'd be silly. Yep. Beautiful. Unknown. Oh no. What? Oh, come on. That function should definitely exist. I'm like, did I name it? I named it something ridiculous. Terrible. Now we're going to have a different error because I renamed it for everybody else. Actually, no, just because I didn't re-export it under any name. Beautiful. Well, okay, what's broken now? There's like a limit to how many things can be broken, right? Yeah, you know, it's the thing where you run it again because, like, you know, maybe the second time you run it, it works. Even if the first time it didn't work and you didn't change anything. I think that's how religion has started. Trunk 32. Well, wait a second. Hold up a second. That is in the at function in... Oh god, this doesn't import types either, does it? Now, this took a lot more time when I was writing it, and you're getting the preview of what it's like to debug Prolog, which is to say, it feels really good, and it's very satisfying. And it makes you really glad that you decided to use Prolog, which, to be clear, I can only complain about so much because, like, I did, but it's not a language that you should write cryptographic code in. Plain text spelled in that way, huh? Well, one, it's actually named input text now, huh? Counter. Oh, where am I calling it counter? Oh, I'm calling it counter there, huh? Yeah, there it is. There, we get that key stream. Beautiful. That should be better. Let's see here. Oh God, do I actually? Right. All of these names are wrong. They're terribly wrong. Is that even closer to right? It's probably not, because that's also wrong. Okay, beautiful. What else is broken? That's broken too, huh? Wait a second. Why would... Oh, no, that would be in this folder, huh? Cha-cha 20 block, but that's exported. I'm pretty sure it's exported. And it no, it's not. To be fair, most of these would be errors in languages other than Prolog too. They're not like specifically Prolog's fault. The fact that it only like spoon feeds you one at a time kind of is Prolog's fault, but it's not an uncommon problem. Oh, I'm foolish. So remember how counter is C0 and C1, but the actual value that we pass happens to be an integer. So one of the things that we have to do is we have to turn that integer into something that can be directly used as that counter. That would look like this. This is, of course, getting the part that is less than getting the part that's less than 2 to the 32 and the part that's greater than that. And we, oh, it doesn't. I knew there'd be bugs. I didn't know there'd be this many. I'm learning a lot about how many bugs I can put into one program. I guess there are probably people who like the chaos. I guess I should be introduced to them at some point. We ostensibly are calling... Oh, we're not... Jeez, awful, huh? There, okay, we're back to the part where it just returns false. Or rather, it just loudly complains that false. So we're just going to quickly binary search for that. There are faster ways to do this, for the record. But this is the way that I know how to do it. Okay, so it doesn't get out of xcha-cha poly 1305 encrypt. Let's see. It does get there. Doing pretty good. It gets all the way past... oh wow, it's getting pretty far actually. What happens here? It does get to that function? Yeah, okay, it does. Right. Okay. So it might be dying in Cha-Cha 20 cipher. That's what it looks like. Yeah, like for what it's worth, it comes with a debugger and it's a good debugger. This is just what I prefer. Right. Okay, so let's take a quick look at how I coded this before. I noticed that there's no base case. Right, so we got to deal with the case where there's no input text and also no, or there's no input text, which we then just map to there also being no output text. Okay, so we've now done that. We'll go back up to the implementation here. Okay, it's still not making it out of that, huh? We're learning a lot about what it feels like to debug Prolog, which is, again, just as a reminder, it feels bad. So it doesn't appear to be returning from that, is what I'm getting here. Oh, right. The function name is different in this version of the program than from my original one. Okay, so now we're doing pretty good. We're getting to the exit point. As you can see, this thing is held together with duct tape and more duct tape. We'll close all of these, prompting to be saved. Yes. So now we have here the input here, which is AAD Pyrex. We are generating this ciphertext. As you can see, we have a nonce. The nonce is selected at random. We have a tag. This tag is genuinely generated from my message. We're going to quickly demonstrate that. We will open this to the side. That looks good. Well, maybe it does. We don't currently need to, yes, we don't currently need to re-encrypt it. We will start it again. We will make sure that the round trip is still good. Yep, round trip is the same message as before. We'll wrap it so we can see. There you are. And we'll change this just like that. And the program loudly and violently crashes. Beautiful. We can also change it like that. Yep, we can also attempt to change the ciphertext. Loud, violent crash. Beautiful. And of course, we could change our message to be something much longer. And we'll toggle word wrap. Let's see. Oh no, is Python... Oh wait, this is a Microsoft... Right, this is my Microsoft environment. They alias specifically the Python 3 command on Windows. It's so good. Do I want to paste... Oh. Windows, come on. Right, okay, there we are. 92 bits of text, or sorry, not bits, bytes of text. Right, that should hit another chunk nicely. Now we'll see if it does round trip. Oh, wait a second. Oh, I'm being a doofus. I forgot to actually... There we are. We've changed the message now. Now, if we look at the round trip version, we see... Yes, beautiful, which is good. I tested that case. Now, as a reminder, there are a few things here that you shouldn't do. One, you shouldn't write crypto code in Prolog. Two, this is not how you should store a key. Three, you probably shouldn't write your own cryptographic code most of the time. There's really no reason to do it. Yes, let's see. What else here is wrong? This probably isn't how you should handle errors in SWI-Prolog. I wish I could tell you how you are. Um, and I would say that like the total lack of algorithms that enforce the amount of time that they take in Prolog is kind of just a non-starter. Probably the most iconic case of that being a problem in this program is in, we'll go to somewhere in this file. I don't know. It becomes very hard. Oh, yeah. Here it is. Here it is. Yeah. So, oh wow. If I turn it to Python, the world becomes difficult. We'll turn it to Prolog right here. So, expected tag is bytes, so it's a linked list. Tag is also byte, so it's a linked list. So, we're doing a different pointer comparison for every byte, which means that, let's say that our tags are like this. Yep. So we've got one that's all zeros and one that goes up. So if we were to compare these two like this, we would die on the first byte immediately. That's the fastest way to lose. On the other hand, let's say that we have it something more like this. We die on the fifth byte. So if we imagine these taking a whole second, which they don't because this is not the 1970s when Prolog was invented. If we imagine these taking a whole second, you could be able to tell that you had most of the bytes to tag right, but you had one wrong just by seeing how long this takes. And to give you an idea of that, like just to look at the ciphertext file one more time. The tag's not short. Like, if I were just trying to brute force a tag that would make my message work, I would be able to count seconds really easily in order to figure out that the first byte needs to be 67. And all I'd have to do is send you 256 messages. Now, in most languages, even though, to be clear, you should still use constant time comparisons for strings, you should use a comparison that takes the same amount of time no matter how big your string, that takes the same amount of time for any given tag. Tags have a maximum size and they take that amount of time. Tags are 128 bits, as you've probably noticed. Yeah, if you always are comparing 128 bits at once using some safe size insensitive comparison algorithm, you're doing good. Even if you're using like an algorithm that operates in blocks of 64 bits or 32 bits, which is overwhelmingly likely to be what your computer uses on any modern processor, that's not great, but it's a little bit better. I'm not authoritatively able to say that it's as good as doing it the correct way, using a size insensitive constant time comparison algorithm. But Prolog is kind of just in the worst possible case because it's going byte by byte. I mean, I guess the worst possible case would be to go bit by bit because then you'd only have to try 250, or you'd only have to try two values in order to get each bit of progress on this. For instance, you could try one that starts with a 0, one that starts with a 1. You'd immediately be told, no, it starts with a 0. Don't be silly. Oh, God, I've broken the file. Oh, wow. I've broken the file irreparably. I'll make a new one. Yeah. On a system that goes by blocks of... Come on. I'll save it, and then I'll regenerate it. On a system that goes by blocks of, like, 64 bits, which would be, like, something like this amount, they'd have to try this many permutations in order to get a resolute yes. That being said, I'm making it sound like I endorse this, and I am not qualified to endorse such a thing because that goes directly against the consensus. At the same time, I wonder about it, whether you can get away with the going by 64-bit blocks given the amount of information that leaks, which to me seems very high in the case of a hit and basically 0 in the case of a non-hit. I'm tangenting immensely. My hope is that having seen this, you understand a little bit more about how this crypto system works. And also, my hope is that you understand a little bit more about why Prolog is practically pretty painful to use and probably not a good language to do hobby projects in unless they're specifically designed for the kind of thing that Prolog is good at. Prolog is basically a database language that is untyped and that allows you to do a handful of other things pretty badly. And I think that that's the impression I get having, again, pulled it out for this project. I certainly don't think you should use anything like this, but if you insist on doing so, you now have seen enough code to make the attempt. Good luck.